Okay, so let's welcome our third speaker in the afternoon, Professor Junbin Li from Zhongshan University. The title of his talk is A Construction of Collapsing Spacetimes in Vacuum. Yeah, let's welcome.
Okay, thank you. Thank you for coming, and I would like to thank the organizers for inviting me here again, and thank you for introduction. So today I will talk about some older work of mine about the construction of collapsing spacetime in vacuum, which is about in the field of general relativity. Okay, now, so the general relativity is a theory of gravitation introduced by Einstein. It is a theory about using the four-dimensional Lorentz manifold to model the gravity. So the Lorentz manifold should satisfy the Einstein equation, which is this is the Einstein equation. So the left-hand side is the Einstein tensor. Right-hand side is the energy momentum tensor of the vector field. And when we set t equals 0, and we call this equation the vacuum equation, then it is equivalent to the Ricci flat of the Lorentz manifold. Now we have some very special and important solutions in vacuum. So the first one is the Cauchy spacetime, which is flat, complete to any directions. And the second one is the very important black hole spacetime, discovered just 1 year after Einstein's discovery. It is called Cauchy spacetime, which is following form, and m is a constant, which is a parameter. So if we this solution will be used to model the a spherical symmetric star, the outside spacetime of a spherical symmetric star, and yeah, but later I will talk about it is about the story of black hole, and the next solution is the curved spacetime, which is very complicated compared to the above two thing. It is a rotating black hole spacetime, which is have two parameters m and a. M is the mass of the black hole or the star, and a is the angular momentum per unit mass. Okay, so when we set a equals to 0, then the curve metric reduced to the Schwarz metric. Okay, so this is the special this is the special solutions, and well, the Schwarz solution is a very good model to introduce the black hole. So we just need to do some very simple coordinate transformation, like the ingoing Finkelstein coordinate VR. Okay, V equals to T plus R star. R star is this guy, R plus 2m log R minus 2m. Then you can do this coordinate transformation. You can see the G takes this form. Well, the differences is in this form, the metric coefficients degenerate at R equals to 2m. Of course, it degenerated at r equal to 0, it is a curvature singularity, but at r equal to 2m, the curvature does not blow up. Okay, so after we do the coordinate transformation, we can see that the r equal to 2m is not a degenerate point, okay, because you have a 2 here. So now you can draw the picture here. Yeah, so well, it is complicated, but let me just tell you that it has a very special region here. Well, corresponding to r less than 2m. Okay, so this part is r larger than 2m, and this part is r less than 2m. Okay, so here is r equal to 0, which is a curvature singularity. Okay, and so this part is called the black hole region of the Schwarzschild spacetime. It is because if you start inside this region, for example, at this point, and you begin to travel, and in general relativity, you can only travel along time-like directions, which is inside the light cone here. So if you travel here, you can see you cannot go outside from r less than 2m region. Okay, so you can only go to the r equal to 0 region. Sorry, go to the singularity r equal to 0. So you cannot go outside again. Once you go inside, then you cannot go outside. So this region is called the black hole region, and even light cannot escape from this region. So this is the black hole region. Okay, so we have a more complete picture of the maximum extended Schwarzschild, because if you use this coordinate, you will find that so this coordinate cover these two region r larger than 2m and r less than 2m, but you can just by simple computation, you can see this boundary is a regular boundary. So by a more coordinate transformation, you call the classical extension, the maximum extended Schwarzschild looks like this, and the before picture here, it is just this part. Okay, you can extend the spacetime here, and this is a complete extension of the Schwarzschild. Okay, it cannot extend more. Now, in Schwarzschild, there are two symmetries in Schwarzschild. One symmetry is the spherical symmetry, and the other is the staticity. Okay. Staticity means that the metric coefficient does not depend on t, and there's no the cross term dTdr coefficients is 0. Okay. So in this case, it is a static. It represents a static space-time. Okay, all things does not change. So if you try to refract the time, and the black hole will become white hole. Okay, it is just a theoretical thing, but yeah, a mathematical thing. Okay. So in the black hole, nothing can escape, and in white hole, well, things just change. So this is the white hole region of the Schwarzschild. Okay. Well, let me just show you some definition, but in a very informal way, because it involves many details. Okay. So the first thing is the motivation is to define a black hole region in a very general space-time, not just Schwarzschild or curve. Okay. So by asymptotic group flat a space-time which is 4-dimensional Lorentz manifold, okay, satisfied, for example, the Einstein equation, and we call this space-time is asymptotic group flat if it approach Minkowski, okay, along space or null directions. Okay, so this is true in Minkowski. This is true in Schwarzschild because you just need to let r tend to 0, then you can see this is just the Minkowski metric. So it is an asymptotic group flat. In space and null direction, but not timeline direction. For a asymptotic group flat spacetime, you may be able to define the concept of the future null infinity, which is the ideal points of the future directed null geodesics. For example, you just in the Minkowski space, here r equals to 0, e equals to 0. Well, you may choose a null geodesics and do some conformal commodification, something like that, and you have a ideal boundary here. Okay. So this is the ideal boundary, which is called the future null infinity. Okay. So the future null infinity is just something. Is the endpoint at infinity of the null geodesics. Okay, so once we have a well-defined future null infinity, we can define a black hole for any asymptotic group flat spacetime, and we have a well-defined null infinity, and we require the future null infinity to be infinitely extended or complete future null infinity. Okay, I think this concept is very much involved, but yeah, you just mean that the space-time is a global. Okay, the space-time as a solution of Einstein equation, it is a global existence. Okay, the solution is global with respect to the time at infinity. Okay. So under this condition, we can define the black hole region to be the set of points in the space-time which is not in the path of the future null infinity. Okay, so the points inside the black hole, okay, it is not in the path of the infinity. So any future directed time-like or null curves cannot reach the future null infinity. Okay, so nothing can escape to future null infinity. So future null infinity is just something in physical just means a place we observe some phenomena deep inside the universe. Okay. So yeah, this is so the black means that no light can escape to reach the future null infinity, and we are sitting at the future null infinity, so we cannot see the light coming inside from the black hole. So this is the definition of black hole. So well, let me mention that precise definition of this thing can be found in classical textbooks. One classical method is to use the conformal commodification by Penrose or Descartes, or Christodoulou has a version of defining such things without using conformal commodification in his survey paper in 1999. Yeah, this part is just the motivation is to define black hole in general space. Okay, now the main problem here is now we know this Schwarzschild black hole is static, so it has a white hole region. So the space-time, it has a black hole initially. Okay. So the question is, we want to ask how the black hole can form. How the black hole form from a regular dispersive initial state. Okay. So if we start from a initial data, so because the Einstein equation is a hyperbolic type in suitable coordinates, so we start from some initial data, which is regular, complete Riemann manifold, and also it is a dispersive initial state. Well, by this maybe I mean that the initial data do not contain any black hole, something like that. Okay. So it starts from a initial state, which is not in a black hole. So and involve these initial data using the Einstein equation, and we ask, can a black hole form, or how a black hole form from such initial data? Okay. So let me call this problem a gravitational collapse. Okay. So the complete picture of a space-time of gravitational collapse, well, means I think means the following things. So the first thing is it should be a development of a complete asymptotic Griffith Cauchy data. By this I mean this should be a solution of Einstein equation. This should be a solution of Einstein equation from a initial data. It should be global hyperbolic, okay, from a non-compact asymptotic Griffith Cauchy data. And okay, it should start from a dispersive state. So to the past, it should be causally geodesically complete. Okay, to the past, you should have a complete time-like, complete null geodesics. So in an informal way, it do not contain a white hole. So if you start from a white hole, it's something like that. You start from a Schwarzschild. Okay. Initially, it has a brown. Okay. Like that. Now, to the future, it should end by a black hole. Okay. So in this case, once we want to identify the black hole in a space-time, I require that the space-time should be, the future non-infinity of the space-time should be extend infinity. So the solution should be a global solution to the Einstein equation in a suitable sense. Okay, and in this case, this thing called event horizon exists in this space-time, and the event horizon is just the boundary, topological boundary of the black hole region. Okay. Now the Penrose diagram can be depicted as this form. Okay. So we start from a complete thing. So the below is something like Minkowski, and above something like Schwarzschild. This is this problem. But let me mention that by now there are very few examples. Well, the first example is just the Hammer-Snyder, the collapse of the homogeneous dust collapse. So I just this is a screenshot from the movie of Hammer. So, people would remember this day. So he evaluated the whole collapse for spherical symmetric homogeneous dust collapse. Okay, and showed that a Schwarzschild black hole eventually forms, and of course there will be a singularity in it. So his solution looks like this. This is a dust energy momentum tensor. perfect fluid with P equal to 0. Okay, and it is homogeneous, so the rho at initial data, the rho is constant in some region and 0 outside some region. So it is the collapse of a dust ball. Well, it can be computed that the inside it is just the Robinson-Walker solution, and the outside is Schwarzschild, and you can just glue them here, but it is not a smooth solution, but it is a weak solution to the Einstein equation. So the outside is Schwarzschild, so here it is the Schwarzschild R equals to 2m, Schwarzschild R equals to 2m. So initially there are no black hole, okay, and along the evolution of Einstein equation, there will be a black hole form here. This is the black hole, and this is the black hole region, and all the things go inside the black hole and then collapse to R equal to 0. Okay, well, let me just make a remark which is actually not tightly related to today's talk. And well, if one studied the inhomogeneous initial dust distributions, and Christodoulou found that it can lead to the formation of so-called naked singularities. And in this case, no black hole forms for this solution. Okay, its end state is not black hole, and Peng gave a lecture on his paper at BIMSA. Yeah, okay. And yeah, and someone remind me that you know, Gu Chaohao had also studied this case in a Chinese. Well, he studied the inhomogeneous dust, and he find that the singularity can form also shell causing singularity and shell focusing singularity. He find out some these cases, and but I think he also mentioned the possibility that the singularity, the central singularity forms can form before the black hole. But I think he did not compute the null geodesics from the center. Okay. So now let me just go to another method field, which is the spherically symmetric Einstein scalar field. So it is not. I think in general relativity we have a theorem which is called the Birkhoff theorem. Okay. This theorem says that all spherically symmetric vacuum solutions are Schwarzschild. So if you want to study such a complicated system, maybe you want to impose the spherical symmetry. But in this case, you found that you find out that this is Schwarzschild, so nothing to study. So well, to overcome this difficulty, okay, people introduce a toy model of the gravitational field, which is the massless scalar field. So in this case, T mass, the energy momentum tensor looks like this, and phi is a function and satisfies the wave equation. Well, this is a result of Christodoulou on the formation of black hole, and well, let me just describe this result. He studied the initial value problem of the initial data is given on this light cone, and once we can find two spherical sections, so in spherical symmetry, this is a Cauchy spacetime, so each point is a two sphere except this line. So on this line, every point is a point, but in the outside region, every point is a two sphere. So between two spheres, okay, if the mass content is sufficiently large, okay, so initially, if the mass is sufficiently large in some sense, okay, then along the evolution of Einstein equation, there will be a black hole region, something here, okay? So a black hole can form once the mass content is sufficiently large. So using this this spacetime, the Fermat proved that by some cooling techniques. He showed that he can construct a smooth collapsing spacetime in the sense I just mentioned. Yeah. It is the spherically symmetric Einstein scalar field solution of the Einstein equation. So this is the metric, and this is phi is the matter field. So this spacetime is causally geodesically complete to the past. And the second one is just saying that it is a global hyperbolic spacetime. Okay. And the third is saying that it has a black hole region. Okay. It has a black hole region. So inside the black hole, we will have a singularity. Okay. And the last statement is that the future non-infinity can be extended infinitely, so that we can say we have a black hole. So the black hole is bounded by the event horizon. So this is the result of the Fermat in spherical symmetry. Okay, now the problem is, we just ask, how about vacuum? Okay, so because of Birkhoff theorem, you should consider this problem outside spherical symmetry. Okay, now outside spherical symmetry, it is not easy to identify black hole because it is not a priori known that a solution can be solved globally. Okay, this is a global existence of the nonlinear hyperbolic PDE. So in this case, Penrose actually, in order to prove his singularity theorem, he introduced the concept of closed-sharp surface. Okay. Here, a closed-sharp surface is this thing is a two-dimensional in a four-dimensional spacetime. It is a two-dimensional spacetime sphere such that it has two normals, and you compute the expansions or the mean curvature. So both mean curvature are negative. So this is a closed-sharp surface. In a flat spacetime, for example, in Minkowski, one should be the both two mean curvature. One is positive and the other is negative. So it is not a normal condition. Okay, the closed-sharp surface. Okay, now Shen Yao. So the problem will be so once we have a concept of closed-sharp surface, we will go to the problem that we start from a regular dispersive initial state and involve the equation. We just want to find out that whether and how the closed subsurface form. Now Shenyao showed that on a initial data, okay, if the matter field is condensed enough, then a trap surface they in fact prove the modes, the most outer trap surface. Yeah, let me just ignore this thing. So when the matter field is condensed enough, then a trap surface is presented on the initial data. But it is not an evolutionary result. And Christodoulou discovered a mechanism of the formation of trap surface in vacuum from dispersive initial state. Okay, so the solution he constructed has passed complete. It is a path geodesically complete, or well, no trap surface is presented initially, like that. And the mechanism is the focusing of sufficiently strong incoming gravitational wave. And maybe you can compare it to the collapsing shell, okay, of dust or of some fluid. It is just a collapsing of well, gravitational shell. Now, from PDO point of view, this is the first result of the long-time dynamics of Einstein equation with large data without any symmetries. The method he called his new method is the short pulse method. Okay, this is Christodoulou's result. So let me just impose initial data on this cone. And this cone from the vertex to somewhere, and this is the Minkowski, and the essential initial data is given on these plots. Okay, some parameter u bar from 0 to delta. Oh, and this delta we impose that the chi hat, which is the chi hat, it's just the trace V part. Of partial u bar G. Okay. G is the metric of the spherical sections of this null cone. Okay, well, something like that. Has a very special ansatz. And the most important condition is that the energy, the incoming energy has a lower bound related to the spherical section. Then if delta is sufficiently small, this is the requirement from the PD part to guarantee the existence of the solution. Okay. And then the solution of vacuum Einstein equation extends up to the place where a curved subsurface formed here to the future. Okay. And because the energy has this lower bound and the trap surface, the area of the trap surface has a upper bound. Okay, you have the more energy you have, and the smaller the trap, the smaller the black hole you will have. Okay. So this is those results, and well, let me just take another twist to this topic, and yeah. So Unlook show this result, but yeah. So Christodoulou's result is about by the focusing of a very strong incoming gravitational wave, and Arnold's result, okay, they are producing the sharp surface by the focusing of a very mild gravitational wave. Okay. By this we mean, if you look at this thing, you will see that this is chi hat. Chi hat is just the derivative of G, So this means that the derivative of G is it belongs to L2. Belongs to L2. Okay. So the mildness means that the G belongs to a higher regularity space. So in Chrysodoros, yeah, this thing, it's just saying that chi-hat belongs to, for example, L2 delta, and in Anlux belongs to 8 something like H. Okay. Yeah, this is H. No. Yeah. Yeah. This is H0. So this is higher regularity. Okay. So it is a mild gravitational wave. And later, by employing the Einstein scalar field system, and by replacing the interior part, originally it is Minkowski, and I just replaced this part by a naked singularity solution, I just mentioned before, and we are able to show that the Chap surface formation is the solution is instability to Chap surface formation under C1 perturbation. Okay, under C1 perturbation. It means that we only need to this result they requires that the chi-hat H half is large. From C. And this means that the C1 norm of chi-hat, the C0 norm of chi-hat is small. Okay. And and recently I show a more regular instability in the same norm, in the same norm of this instability, but he replaced the interior part by a self-similar naked singularity. I do not want to explain that. And we are also studying the Einstein-Euler system to study some instability of naked singularity. And the basic method comes from Chrysodoros' work. Yeah, just test. So now, and after Chrysodoros' work, we want to construct a space-like Cauchy data instead of here it is a characteristic data. We can construct a Cauchy data, space-like Cauchy data. So the difficulty is that a space-like Cauchy data should the three-dimensional Riemannian manifold with three-dimensional manifold with a Riemannian metric G and a second fundamental form K. So they are not free. Okay, they should satisfy a constraint equations, something like that, a nonlinear elliptic equation. Yeah. But anyway, we proved the following result. Given any mass, and any very small epsilon, then we can construct a space-like Cauchy data, such that, well, the Cauchy data, well, let me just say that, let me first look at the last statement, okay? And this data contains no trap surface, but the trap surface will form to the future of this data. Okay, so we construct a data space like Cauchy data, and no trap surface here, but in the future we will have a closed trap surface. Okay? So this is something collapse. And the other statement is just some technical detail. But let me mention that one thing that this initial data we construct has a very special property that the outside part, very far away part, the outside part, is isometric to the curve data, with this curve. This curve has parameter MA, which is close to the given mass parameter, and the A is very small. Okay, so this is a very special property of this thing. So now, but all Pierce works, okay, outside spherical symmetry are not about black hole in just trap surface. Okay, so let me remind you that to identify a black hole, we need to solve the solution globally, and we have a infinitely extended future non-finity. Okay. In this case, we will have a regular event horizon. So this is the more recent result, and we can construct a solution of vacuum Einstein equation satisfy the following conditions. Actually, these statements is just the statement that the solution we construct is a collapsing spacetime. So the first thing is that it has a complete future non-finity, or its future non-finity can be extended infinitely. Okay. And in this case, M will have a black hole region B bounded from the past by regular event horizon. Well, the second statement is that it is a future development of an asymptotically flat Cauchy data. Yeah, it is a solution of vacuum Einstein equation from a complete asymptotically flat Cauchy data. Okay, and more importantly, this Cauchy data does not intersect the black hole region. Okay, it is not no points on the Cauchy data lies inside the black hole. Okay, and one more thing is that it has a topology R3. And the last statement is the same to the statement before, that it is isometric to curved spacetime near the whole future non-finity. And the parameter of curve is sufficient, is close to a given parameter m0, and the angular momentum parameter is sufficiently small. Okay. So this result covers the before result. Okay, because that in the spacetime we constructed, there is a closed subsurface inside the black hole. Of course, in the future development of sigma, and because the sigma, the intersection of sigma and B is empty, and all closed sharp surface must lie inside the black hole. So sigma does not contain any closed sharp surfaces. Okay. So this is a result describing the collapsing using the black hole, but not only sharp surface. Okay, this is the picture. This is a difference. So the before work is just a Cauchy data here, and no sharp surface here, and yeah, you just need to solve the equation, and the equation exists here. So inside the black hole, so this is a sharp surface. So you have a solution here, and of course here. Okay, but you do not know this part. Okay, if you want to say a spacetime have a black hole, you need to have this part. Okay, but I don't know this part in that work. Okay, in the more recent work, we can construct spacetime containing the whole future non-infinity and has a black hole region here and the regular event horizon, the path boundary of the black hole. Okay. Now, I should mention the more recent work by Kane and Unger that they also constructed a collapsing spacetime in a different way, such that the mass and angular pointer outside curve can be specified explicitly. Okay. Well, in our before work, okay, yeah, the outside curve, the pointer MA is sufficiently close to M naught 0. Okay, but you cannot, yeah, but you cannot specify MA. You can specify M naught, and the resulting MA is sufficiently close to M naught 0. And in their work, they can just specify explicitly the curve parameter for A sufficiently small. Okay. Now, as a corollary, it can be Schwarzschild. Yeah, this is the advance as compared to our works. Okay. Yeah, this is the maybe let me just make some comments on the proof. Okay, so now the first step is to just consider this is the Christodoulos picture, and you solve the characteristic initial value problem here. Okay, and you solve as in Christodoulos, but we need an additional condition here. The incoming energy, this is the incoming energy, is for n naught. Well, by this condition, I mean that it is not, this for n naught does not depend on the angular parameter of chi hat. So the incoming energy is the same along every direction, up to a very small error, delta to the minus delta to the half. Okay.
Thanks, Professor Li, for his very beautiful talk. So, any questions from audience?